Take a circle and randomly select 3 points on the circumference. Now join those points to form a triangle. What is the average area of a triangle constructed in this way? Trying to solve this immediately would be very difficult, so let's look at some easier problems and work up to this one. Firstly, we have to figure out how to derive the area of a circle. Many of you already know that the area is pi times the radius squared, but how do we actually derive this? The area of a circle isn't quite as simple as the area of a rectangle, which is just the base times the height, and there's no easy way to compare them. But something we could do is make a lot of parallel cuts in our circle, and compare the area of each segment to the area of a rectangle. Each of these segments can be approximated as a rectangle, and since we can find the area of a rectangle, we can add up the areas of all of these rectangles to approximate the area of our circle. And if we were to cut up our circle even more finely, our approximation would be better. In fact, we could start cutting so finely that our rectangles actually become lines. So now we're adding up infinitely many lines to get the area of our circle. We call this process integration, and we denote it with this funny S symbol here. Now, to add up all these lines, we actually need to know how long each line is. For any given line at distance h from the centre of the circle, we can find the length of that line using Pythagoras' theorem, which gets us that each line is equal to 2 times the square root of r squared minus h squared. So we can find the area of our circle by integrating this expression with respect to h, where h goes from negative r to r. Now this video won't go over how to calculate integrals, we're just going over how to use them to solve problems. So we're simply going to fast forward the calculation, and at the end we get pi times r squared, which is exactly the area of a circle. Now that we know the area of a circle, there are 2 questions we can ask that will get us closer to finding the average area of an inscribed triangle. 1. What is the volume of a sphere? And 2. What is the average width of a circle? Let's start with that second question. Firstly, we construct a rectangle which has the same height as our circle. And we construct it in a way that our rectangle and circle have the same area. We label the width of our rectangle A, and this will be the average width of our circle. To find out what A is, we mark the height B and note that B is equal to the diameter of the circle, or 2 times the radius. Since the rectangle and circles have the same area, the area of the rectangle is pi times r squared, which equals A times B, which equals 2r times A. Using a little bit of simple algebra, we get that A is equal to pi r over 2. And this is the average width of a circle. Now let's move on to tackling the volume of a sphere. We can start by making parallel cuts in our sphere, splitting it into many segments. Note that each segment can be approximated as a cylinder, and adding up the volumes of these cylinders will approximate the volume of our sphere. And again, we can make these cuts infinitely thin, turning our cylinders into circles, thus changing our addition of cylinders into an integral of circles. And again, using Pythagoras' theorem, we can find the radius of any circle at any given height, and therefore find its area. And again, we'll take the integral of this expression with respect to h, as h goes from negative r to r. And skipping through the calculations, we get that the answer to this integral is 4 pi r cubed over 3. And this is the volume of our sphere. Now something we could ask is, what is the average width of a sphere? Firstly, we have to construct a prism that has the same volume as our sphere. And it's important to note that our prism has to have the same shadow as our sphere, simply meaning that when we look at both shapes from above, they look like the same shape. In this case, the shadow is a circle, which means our prism is in fact a cylinder. Now this cylinder will have the same radius as our sphere, and we'll label its height A, which is the average width we're looking for. Now given that our cylinder is a prism, its volume is equal to the area of the shadow times A. And given that the shadow is a circle, we know its area is pi times r squared. And we know that our cylinder has the same volume as our sphere, which is 4 pi r cubed over 3. So we can now use some simple algebra to get that A is equal to 4r over 3, which is the average width we're looking for. Now let's move on to one final small problem before trying to tackle the big problem. We'll be taking this wedge-like shape here, and again we'll ask what is its average height. We'll define the base side length as s, and from there derive the side lengths of other edges of the shape. Firstly, we'll need to find the volume of this shape, and as normal we can chop it into very thin slices and take an integral. In order to take an integral, we're going to need to analyse the shape of these slices. Here is the example of the slice some distance x along the length of the shape. Using some simple geometry, we can find the relevant side lengths of this slice. Now we need to find the area of this slice, and to do so, we're going to chop it into thin strips and take an integral. To do so, we're going to have to find the length of each of these strips. Looking at the strip some distance y along the length of the slice, we can use some geometry to find its length, which is just x plus y. Now we are able to use an integral to find the area of each slice, which is the integral as y goes from 0 to s of x plus y dy. And since this integral gives us the area of the slices, and taking an integral of the slices gives us the volume of our shape, we can find the volume by taking an integral of this integral, which gives us the integral as x goes from 0 to s of the integral as y goes from 0 to s of x plus y dy dx. And again, we're going to fast forward through the calculations here. The integral itself isn't too difficult. If you can integrate, you'd be able to integrate this pretty simply. The important thing to note is that we use the double integral to find the volume of our shape, which turns out to be s cubed. Now let's move on to finding the average height. As we established previously, the average height is simply the volume divided by the shadow. And as we can see for this shape here, the shadow is in the shape of a square with side length s. So quite trivially, the area of the shadow is s squared. So the average height is volume over shadow, which is s cubed over s squared, which is s. And this is our average height. Now we can tackle the problem from the start, which was what is the average area of a triangle inscribed in a circle? We'll start by connecting each vertex of the triangle to the centre of the circle, splitting our triangle into 3 smaller triangles. We'll label each of these angles A, B and C, and we'll label the radius r. Note that the sum of the angles A, B and C is 2 pi radians, and that all of these angles are non-negative. Also note that given a triangle with an angle theta, and the two sides adjacent to theta are x and y, the area of the triangle is xy sine theta over 2. We can use this area formula on each of the 3 smaller triangles, where x and y are both equal to r, and theta is equal to a, b or c. This will give us the total area of our large triangle, which is r squared over 2 sine a, plus r squared over 2 sine b, plus r squared over 2 sine c, which we can simplify by factoring out r squared over 2. Now, something to consider is if the centre of our circle lies outside of our triangle. Here, we can still connect the vertices to get 3 smaller triangles. But as we can see from our shading, we would actually want to subtract the orange triangle instead of add it. But this resolves itself because the angle C is actually this large angle on the outside, which is greater than pi radians, which actually means that sine of C is negative. Thus, leaving our formula as is does indeed subtract the orange triangle to get the area of the triangle we want. So our formula works in all cases. Now, we can rearrange the first equation we have to get that C is equal to 2 pi minus a plus b. Thus, sine of C is equal to sine of 2 pi minus a plus b, which equals minus sine of a plus b. Thus, we can make this substitution into our area formula so that it's entirely in terms of a and b. Now, we can reframe our problem as instead of picking 3 points on the edge of a circle, we actually pick 2 angles A and B. Now our first choice for angle A can be any angle ranging from 0 to 2 pi radians. Now we actually have less to choose from for our second angle B. As we can see, A has already taken up some of the circle, and a plus b can't exceed the full circle, or the full 2 pi radians. Thus b is limited between 0 and 2 pi minus a. And these will be the constraints on a and b when plugging them into our area formula. Now, since we have a formula with one dependent variable and two independent variables, we can actually plot this on a 3D graph. And this graph will resemble some 3D shape. And the three axes will be A, B, and the area. Now, since the height of this shape at any given point represents the area of an inscribed triangle, and we want to find the average area of an inscribed triangle, we need to find the average height of this shape. And we can do that by dividing its volume by its shadow. And as we established earlier in this video, we can find its volume by taking a double integral, and its shadow will simply be the area of its base. Now all that's left to do is calculate. As we established earlier, a ranges from 0 to 2 pi, and b ranges from 0 to 2 pi minus a. And the area is equal to r squared over 2 times sine of a plus sine of b minus sine of a plus b. So we can take a double integral of this expression with respects to b and a. An important note here is that the integration with respect to b goes on the inside, i.e. it happens first, because the boundary of b is dependent on a. And again, we'll fast forward through the calculations here, but in the end we get that this integral is equal to 3 pi times r squared, and thus the volume of the shape bounded by our 3D graph is 3 pi r squared. Now let's look at the shadow. In order to find the shadow, we need to look at the graph from earlier, but only the a and b axes. And again, a ranges from 0 to 2 pi, and b ranges from 0 to 2 pi minus a. Thus, we can shade in purple the region containing all possible choices for a and b, which is bounded by the axes as well as the curve b equals 2 pi minus a. And since our curve is linear, our shaded region is a triangle. We can see that along each axis, the length of the triangle's side is 2 pi, and that the axes are perpendicular, which means that the area of this triangle is 2 pi times 2 pi over 2, which is 2 pi squared. And this is the value of our shadow, which means we have enough to finally answer our question. Given a circle of radius r, 3 random points selected on the circumference will form a triangle. The average area of such a triangle is equal to v over s, which is equal to 3 pi r squared over 2 pi squared, which is equal to 3r squared over 2 pi. And this is our solution. Thank you all for watching. I hope you learnt something interesting, especially about the usefulness in using double integrals to find the volumes of shapes. Now, if you ever find yourself in a predicament where you need to calculate the hypervolume of a 4-dimensional manifold, well, I think you'll know what to do.